let P, Q, R, S, T, maybe more than 2 statements are given, and Q also having P, Q, R, S, T, and so on. Be 2 propositions. B, 2 propositions where small p, small q, and so on are proposition variables. That means we use as a statement. So if a proposition variables variable p, q have the same truth value, in every possible case. In every possible case, so the proposition you use then the propositions are called logically equivalent. Or simply equivalent. We denote it as P having small p, q are variables, and this is logically equivalent to q having p, q, and so on. So P is said to be the logically equivalent. So first we construct the truth table for capital P, then construct the truth table for capital Q. Then we check both the column having same truth value. If both the column having same truth value, we can say that the 2 propositions are logically equivalent. First we construct truth table for P, construct the truth table, then we construct the truth table for Q, check both the columns for P and Q having same truth value, are said to be logically equivalent. Said to be logically equivalent. Understand? Just we have 2 propositions. Propositions means compound statement. Small p, q represent the simple statement. That means small p we denote as Ram is a good boy. Second, q be the statement represent the Sohan is also a good boy. And we make a compound statement P and Q. Ram and Sohan both are good boy. So this is capital P. Similarly, for capital Q, we have two statements, and we construct the truth table, and on the basis of truth table, we check the columns. If both columns having the same truth value, there we say that both the statements are logically equivalent. Understand? We can understand with the example. Okay, Vikram, Aryan, Ashna, Ayushi, raise hand. Chelsea, you are not responding. Yes, good. So we take an example. Use the truth table. Use the truth table to prove P or Q and R. P or Q and R is logically equivalent to P or Q and P or R. So we write here P and Q in this form. So this is logically equivalent to Q. So this compound statement, this compound complete statement, we denoted as capital P, and this compound complete statement denoted as capital Q. And small p, q, r be the variables. We say that a function of xy. We write as f of xy. So f of xy is the variables, independent. So here capital PQ are the function of PQR, small pqr. So we want to show both are logically equivalent. This sign symbol represents the logically equivalent. So we construct the table according to the statements. So that means we have three statements P, Q, and R. So first we take the column for P, and when we have three statements, that means P, Q, and R. So this means that we have at least 8 rows. 8 rows, that means first column having 4 truth value true, and last 4 truth values are false. For statement Q, we use 2 true value, 2 false, 2 true value, and 2 false value. And for third statement R, we have 1 truth value true, false, alternative. That means true, false, true, and false. Now, according to the question, we see that first we solve the bracket. That means we check the LHS part. So first we calculate Q and R. First we solve the bracket, then we make the disjunction with the Q and R. That means this is our second column for this RHS part. Now we see the RHS part. So for RHS part, first we calculate the P or Q. That means in this column we calculate P or Q. Next column we calculate P or R. And last column we have to calculate complete capital P. That means P or Q and P or R. P or R. So we want to prove that the statement is logically equivalent. That means using the truth table. This is known as the truth table. So we draw the truth table. We know all the connectives. So when we know all the connectives, that means conjunction, disjunction, negation, conditional, and biconditional. Here we use only 2 connectives. That means conjunction and disjunction, and or. So first and represent the truth value. That means conjunction. Only true is true, otherwise false. So we construct true is true, otherwise false. Q and R, we are talking Q and R. So this is false, false, true, false, false, and false. So this is for Q and R. Now we make OR with P. So for OR, we know that only false, 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 otherwise true. So P or Q and R, that means true, true is true, true, false is true, true, false is true, true, false is true, false, true is true, false, false is false. So this is the last table. That means this is the capital P. You can write as capital P. So we want to show that this column is having same truth value with the last column. So now we calculate P or Q. P or Q, that means or having false, false is false, otherwise true. Preet, Kumar. So P or Q, that means true, true is true, true, yes. True, 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 and false, false. Good. All are doing? You may practice. That means, yeah, good. And P or R. P or R, that means P or R. So or, that means true, true is true, 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 and this is false, true and false. Now we make AND. So true and true, 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 fourth, fifth, true, and true, false is false, false, false is false, false, false. Only true, true is true. So we have 5 truth value, true, true. So this is the, okay, done. So we see that means 1, 2, 3, 4, 5, 5 true value, 3 false value. Here also 1, 2, 3, 4, 5 true value, 3 false value. So both are logically equivalent. Hence, we write as hence P or Q and R is logically equivalent. Logically equivalent. So P or R. So you can show by using truth table. Understand? So try to solve all the problems related to truth table. So when you solve more problems, then you can remember all the connectives. So connective play a very important role when you do a single mistake. When you do single mistake, that means erroneously you want to write true, you write wrongly false. That means complete table is wrong. So carefully you use all the connectives without any mistake. Okay. So now we move further. That means you all noted Dharvi, Gaurav Kaushik, Gaurav. Okay, Gaurav, Dharvi. Now, next topic, algebra of propositions. That means we have some law. Algebra of propositions. You remember all the laws? Algebra of propositions. As we study in set theory, we have some law, that is idempotent law, identity law, commutative law, distributive law, associative law. So same laws are here. Here we use the connectives, that means and or negation. On the basis of connectives, we write the laws. So the law number 1, first law is idempotent law. You remember all the laws? Idempotent law. For idempotent law having two statements. First, if P be the statement, so then P disjunction P or P, which is always equivalent to P, and for second P and P also equivalent to P. So here you see that we have only one statement. One statement, that means by proving this as truth table. So when we have only one statement, so number of rows are 2, true and false. So then we write again P, so having true and false. So we write P or P. So that means P or P, only false is false, otherwise true. And for P and P, only true, otherwise false. So we see that this is equal to this, and this also equal to this. So both law we can verify by using truth table. So we can say that P or P is equivalent to P, and P and P also equivalent to P. Understand? Or you noted? Ankita, Ankush. Okay. Now second law. Second law, involution law. Okay. Involution law. For involution law, we have the same two statements. That means negation of negation P always equivalent to P. Negation of negation P is always equivalent to negation P. Having only one statement. So negation of negation P, that means we have a statement P having two values, true and false, and a negation of P, we write false and true, and a negation of negation P, we write as true and false. So negation and negation P is always equivalent to P. Negation of negation P is always equivalent to P. Okay. Law number 3 is identity law. You remember all the laws? Identity laws. So for identity law, we have 4 statements, that means P being any statement, and F is the truth value. So when we make a OR with the F, so is always equivalent to P. For second, P and T is always equivalent to P, and P or T is always equivalent to T, and P and F is always equivalent to F. So we have 4 statements. So P be the statement, F and T represent the truth value. Truth value means T represent truth value true, and F represent the all false values. So for proving this, that means first student want to prove by using truth table. So P, when we have only one statement, so we write one true value and one false value, and F represent the truth value, that means having all false value. So we make OR with F. Make OR with F. That means true false. So true false is true and false false is false. You know that? That means in disjunction only false false is false. So we see that the P and this column having same truth value. So this is equivalent to this. Okay. Similarly, you can prove for second. For proving second P, we have true and false, and truth value T, they have all value having true. So we find out P and T. So true is true or otherwise false. So both the column having same truth value. So you can prove third and fourth similarly. Okay, noted. Gaurav Kaushik, Nikhil, Rohit, Rohan, Samriti, Megha. Okay, Mansha. Okay. Now next law, law number 4. This is commutative law. Law number 4 is commutative law. Commutative law, similarly, we use in set theory. We use the operation union and intersection. Here we use the operation and or. So that means P and Q be two statements. So P and Q, that means P and Q always equivalent to Q and P. And second, P or Q is always equivalent to Q or P. So you can prove by using truth table. So P and Q is always equivalent to Q or P, and Q or P and Q and P. Now law number 5. Associative law. Associative law, we have three statements, P, Q and R. So for first part, P and Q and R, which is always equivalent to P and Q and R. Second, P and P or Q or R is always equivalent to P or Q or R. So this is the law number 5. Similarly, you can prove by using the truth table. That means we prove this table by using three statements, P, Q and R. So you can prove this also. Both are hereditary property. We also discuss in set theory. That means associative and commutative always satisfy in each case. Law number 6. Law number 6 is distributive law. Law number 6 is distributive law, having two cases, that means P and Q or R, which is equivalent to P and Q or P and R. For second case, P or Q and R always equivalent to P or Q and P or R. So you see that here we take the example. This is also the example of distributive law. P or Q and R. P or Q and R. This is second distributive law. This is B part. So we already proved this. So this we already done in this example. So you can solve first part. Okay. Yeah, you can do first part. This part you can do. Next law number 7, complement law. Complement law. So complement law having P or negation of P. P or negation of P is always equal to truth value T, and part B, P and negation of P is always equivalent to false value F, and third C. So negation of true value always equivalent to false value, and D, negation of false value is always equivalent to true value. So this is the complement law. This is the complement law. So you can prove by truth table. P having true and false, negation of P, you write false and true, and we make P or negation of P, or means false is false. Here we see that true false is true and false true is true. So this we can write as true, T. Okay. So similarly, you can prove the remaining parts, and you do not need to prove these parts, because we know the negation of true is false and negation of false is true. And the last law number 8 is De Morgan's law. So we also write De Morgan's law in set theory. Here also we use the De Morgan's law. All you noted 6 and 7. Khushbu, Mansha, Megha, Mohit. Okay. Yeah. Vikrant, Vidhi. Okay, good. So De Morgan's law. For De Morgan's law, we have statement P and Q be two statement. So P and Q, negation of P and Q, which is always equivalent to negation P and negation Q. And a negation of P and Q, which is always equivalent to negation P or negation of Q. So this is the De Morgan's law, law number 8. So we have 5 connectives, or you remember all the 5 connectives and symbols for all the connectives, and the concept of the bracket. When we have brackets in between the statements or propositions, so first we solve the bracket, then so now we move to the next topic, that means main topic. You can prove De Morgan's law by using truth table. Okay, first we can prove as, so when we use two statement, that means P and Q, so you can write as true, true, false, false, because we have two statements, true, false, and true, false, and we write P or Q. P or Q, that means only false, false is false. So true, 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 and false, and the negation of P or Q. Negation of P or Q. So this is false, 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 and true. Now for RHS part, we calculate negation P. Negation of P is false, false, and true, true. And the negation of Q. Negation of Q, false, true, false, true. And negation of P and negation of Q. So negation of P and negation of Q. And means so false, false is false, 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 and true. So we see that both the two columns having same truth value. So both the two columns having same truth value, that means they are logically equivalent. So they are logically equivalent. Logically equivalent. Okay. So second, you can do similarly. All good. Now we move for the next topic. Next topic related to the tautology. That means types of okay. Start tautology. Okay. Tautology. So we have three main topics for that, means tautology, contradiction, and contingency. So for proving tautology, contradiction, and contingency, we draw the truth table, and on the basis of truth table, we check the final table, that is final column of the table, that is called proposition. So a compound proposition, we define tautology as a compound proposition which is always true, which is always true under all circumstances. All circumstances for all possible truth values. For all possible truth values of its variables is called the tautology. Is called the tautology. Called the tautology. So remember, the final column having all truth values are true. That means T. So a compound proposition that means we have three statements make a compound proposition which is always true under all circumstances for all possible truth values of its variable. So variable means P, Q and R when we use three variable. So give the truth value true, always true. You remember this, always true. So called the tautology. So for example, we take one example, prove that the statement P and Q conditional P conditional Q is a tautology. So P and Q are said to be the statement, and this is called the compound proposition. That means we are talking about the final table. So that means in final table you have to calculate this completely. So this is the compound proposition. That means we use two sentence statements P and Q, use some connectives. So then this is the complete proposition, compound proposition. So how to construct this? That means we prove this by using theorem. So we have two statements. The first column we use for P and second column we use for Q, and third column accordingly we calculate P and Q, solve the bracket, and fourth column we also solve the next bracket, and the fifth column we take the complete compound statement. So complete compound statement we take in the last column always. So this is the final column. We write in final column. So we mention in remember, that means this is final column having all truth values are true. Final column having all truth values are true is known as the tautology. So we construct the table. That means we have two statements P and Q. So we take two truth value true and true false, an alternative true false, and make AND, that is true is true, otherwise false. So false. And P conditional Q. What is the meaning of P conditional Q? That means fourth connective. Conditional. In conditional we know that true is true, and second condition true is true. Yeah, TFFT, good. TFFT, no. That means true is true. True false is false, and false sorry, true false is false, and false true is true, and false true is true. This is the, you remember the definition. Definition is that when P and Q are true, then P conditional Q are true, and if P is false, if P is false, then P conditional Q is true. Only P is true, then P conditional Q is false. So remember the definition of force connected? Yeah, good. So now we take again conditional with both the columns. So again conditional, true true is true, false false is true, false true is true, and false true is true. So this is the final column, having all the truth values are true, having the compound proposition having all truth values are true. So hence this is a tautology. Hence this is a tautology. It is tautology. Tautology. Okay. Vikram, noted. Vikrant, sorry. Vikrant, Sukhmeet. Okay. Okay. So this is the first definition, that means definition of tautology. For moving second definition for contradiction. Contradiction. A compound proposition which is always false, which is always false under all circumstances, for all possible truth values of its variable is called contradiction. Is called contradiction. That means in tautology we have the final column, all truth values are true, but in contradiction all values are false. That means final column having all truth values are false is known as the contradiction. Is known as the contradiction. So for example, prove that P and Q and negation of P is a contradiction. Is a contradiction. So this is the compound proposition. Compound proposition. According to the compound proposition, we construct a truth table. So P, Q, and P and negation P. The means we can take one column as negation P, then Q and negation of P, then final column is P and Q and negation of P. So P having two truth values are true, true and true, false. This is true, false, true and false, and negation of P. What is the negation of P? So that means false, false and true, true. So Q and negation P, Q and negation P. So this is false, false, true and false. Only true, true is true, otherwise false. And we make the end with P. So true, false is false. True, false is false. False, true is false. And false, false is false. So final column having all truth values are false. So this is known as, this is known as the contradiction. So this is known as the contradiction. This is the final column. Remember, this is the final column. So final column is you write the complete proposition. That means a compound proposition. So having all the values are false, so known as the contradiction. And a third definition, which is related to contingency. Contingency, so we can define as, just we take 2 minutes for defining third. You note down contingency. Third is contingency, a compound proposition which is either true or false depending on the truth values of its variable. Its variables is called contingency. Some values are true, some are false, is known as the contingency. Known as the contingency, either true or false. That means the final column having mixed value, that means true or false, known as the contingency. Note down the example. You try to a statement P and negation R implies and imply that Q or R is contingency. So try to solve this. Okay, so thank you, students.